Hello, everybody, and welcome to Essential Physics. And this is a very special video because this would be our first lecture where I'll actually be, discussing the textbook or the textbook material. So, this is about the first chapter, that is electric charges and fields, but I'm just going to write electrostatics on the board because essentially that's what we're discussing here in the first and second chapter. So, in this particular video, we'll be talking about what electrostatics is, what really defines our conductivity, what makes an object a conductor of an insulator, and we'll also be talking about what are the properties of electric charge after defining what electric charge is, obviously. So let's begin. Electrostatics. Now, it's not something we encounter as often as something like current electricity. So you could see this light bulb's working, and that is an effect of electric current passing through it. But static, well, we could see that current electricity is moving. That's why it's in a current, right? But you might also have heard the term static current. Have you? Static electricity, if it rings a bell. Okay, let's talk about statics. So electrostatics, you could break it down right here. Maybe I'm placing it right. Yep, two words right there, electro and statics. So electro is something that's related to charge. It is. And statics is something that doesn't move, isn't it? When we say something is stationary, the body is static. It's not in motion. Or more like it's not dynamic. There's no force applied to it. Or so we think. So static is something that doesn't change with time, right? And in electrostatics, we'll be talking about maybe fields, forces, and potentials that arise from charges that are stationary, the effects of static charges. And what is static? So how did people come up with this, right? So, well, you guys might have come up with it on your own when, say, you rub a plastic ruler through your hair, provided your hair is dry, and you can lift up bits of paper. Why does that work, right? So people thought about it. They were like, okay, there's probably some kind of force that attracts it, right? Of course. So the first observed instance is from 600 BC, where there was a man called Thales, I'm not sure how to pronounce it. He's from Greece. And he observed that when he rubbed a stick of amber with silk, it started attracting smaller objects. So what is amber? Well, amber is basically some sort of, it's like a semi-precious stone. Well, maybe not semi-precious, but it's a bit expensive. It's something that people make rings out of. Basically, it's fossilized tree resin in a way. So sometimes if you've seen the rings, sometimes you might find a tiny insect in there, and it's kind of, the insects got trapped in this tree resin, it got fossilized, and now there's an insect in the gemstone. I'm not sure if it's okay for me to call it a gemstone, but it's sort of like a gemstone. It's not as precious as maybe diamonds or sapphire, but it's also not, it's between the two. So yeah, that's amber. People liked it because it's pretty. Yeah, it looks pretty. So you could just Google amber. You'll find it. It's some kind of solid material. And he rubbed it against silk. Found out that it started attracting, well, maybe small pieces of straw or paper. I don't think paper was there, but yeah, I think straw. So in Greek, amber used to be called electron with a K, E-L-E-K-T-R-O-N, and we get the word electricity from electron, right? And that comes from the Greek meaning amber. Let's write this down. I'll write this down. I'm just going to explain it to you. You guys don't need to write it down as such if you're taking notes. But the thing is, let's see. Let's have a series of experiments. Okay. So, based on the simple illustration, this is glass, that's glass, this is wool, and that's wool as well. So, he observed, or let's just, whoever did this observed, that after you rub these two together, and you rub these two together, this particular body attracts this one, and this attracts the same. But these two glass rods do not attract each other. They actually repel each other. And these two repel each other. Okay, now we have that observation. We have another instance. We have plastic rods and cat's fur. So let me just write this down. This is glass and this is wool. This is plastic and this is fur. After rubbing the plastic and the fur, we observe that the plastic repels each other and the fur repels each other, which makes sense. And the plastic attracts the fur and so on. However, we also observe that after rubbing, the glass and the plastic attract each other, but the plastic and the wool repel each other. So you could see that all these are connected in some way or the other, right? And this led scientists to believe, or whoever was doing these observations back then, to believe that there's two kinds of force, attractive and repulsive, right? We have attractive and we have repulsive forces, as you could see. I haven't completed this, but again, repulsive, attractive. Oh, also the wool and the fur attract each other as well. Yeah, right there. So these two kinds of forces exist. And now, what would be similar to this type of force? If you think about it, it's similar to magnetism, right? Isn't it? We have the north and the south. The north and the north repel. The north and the south attract. South and south repel. South and north attract. So we could say that during this rubbing process, something happened that caused it to repel each other and attract each other. And that's caused by something that we like to call an electric charge. And, well, Benjamin Franklin kind of defined it as the two things, well, after rubbing, the glass rod is now charged positive and the other is now charged negative. So he stated that if the scientist back then was like, whatever's on the glass rod is negative and whatever's on the wool is positive, we might have dealt with that convention, but this is what we're dealing with. When we say an electron is negative, it comes from that observation, and I'll tell you about it shortly. But when we say something is negative, it's just a naming scheme. He could have named it north and south if he wanted to, but this is it. Like charges repel each other, and unlike charges attract each other. It's pretty similar to the magnetic pole system. There's a simple apparatus known as a gold leaf electroscope. So basically, this is how it kind of exists. This is made out of metal, and this is, I think, it's a gold leaf, which is very light. So what happens is if this comes into contact with something that is, say, positively charged, right? The electrons would flow in such that this becomes positive, and once these two units are held positive, they repel each other. So we could quantize if something is very heavily charged or not. If the force is high enough such that it goes all the way, it's, highly charged. If it just moves a little bit, it's lowly charged. Coming to conductors and insulators. What are conductors and insulators? I'm pretty sure everyone's heard these words before, right? An electrical conductor, like a copper wire, wood is an insulator. Now, what exactly does this mean? So, let's take the case of electrostatics, since we're talking about that now. Let's say if a spoon was used to rub to your hair instead of a comb, or a plastic ruler, for example. The spoon doesn't attract the particular, paper. And why is that? Well, it's because even if the spoon gets charged, the charge travels through the conductor and goes into our hand. And since we are a conductor, it goes into the earth. The balance of charge is now balanced. And why is this? So, I'll go into details later in the third chapter called current electricity. But basically, when there's a conductor, the charges distribute themselves along it because it's easy for the currents to flow through that material. But for an insulator, the currents just stay at the point where it's charged. So if this is a spoon, this is a piece of wood, if I touch it to a charged body, the whole of the spoon is now charged. It's evenly distributed. But if I touch wood to a charged body, maybe this particular point is now charged. Or plastic, maybe this particular point is charged, not the whole thing, because it's not allowed to flow with ease. I mean, sure, if I have a very high potential, a lot of positive charge here, it might burn through the wood, it might force the charge to go in through the wood, but the wood would prevent it from happening. And you might have seen maybe electricity burning down a tree because of high voltage. This is kind of the effect. The excess energy in the line is now forcing itself through the wood, and the wood isn't allowing it to happen, so it just burns it down in the process because of there's a fight between the electrons on the wood. Now these are the properties of electric charge. So when we talk about properties, it's just okay. What are the defining features of it, or what are the features, right? What's special about electric charge? I say there's an electric charge, so you could say, well, the electric charge, right? There's positive and negative. If I put both of them together, positive and negative together into a body, does it cancel out? Does it just become negative? Does it become positive? So to answer those sort of questions, we need to understand the behavior of these, and for that we need to examine the properties. Additivity of charges. So this basically just states that to a body, if you add 1 unit of charge and then you add 1 unit of charge again, it's going to have 2 units of charge. Obviously depend on the limit of the body, but let's say we have a system where we have 1 point charge, that is Q1, and you have another point charge Q2. So the total system is Q1 plus Q1 plus Q2 worth of charge. And since charge is now positive and negative, if one of them is positive and this is now negative Q2, the total charge is Q1 minus Q2. And if Q1 and Q2 are equal, it's now 0. It's neutral. Electric charge is conservative, or electric charge is conserved. And that means that you can't create it, you can't destroy it. It just exists. You can maybe neutralize it with positive and negative, but you can't produce it. You can't just simply... Let's say I have the same example of rubbing your hair through a plastic comb. You have produced positive, but you've also produced negative, and the negative is on your head, right? And the hair in your head. But the thing is, you can't just produce only positive charge from a neutral body. It's not possible. And that is because of conservation of charge. And I'm talking about the whole, as a sum of the universe. Well, you could say, I've rubbed the hair, but since we are conductors, the negative charge in my hair is neutralized because of the, let's say, electrons flowing into the earth. Yes, but for the whole earth, it's the same. There's positive produced in the plastic spoon or the plastic ruler, but negative is now released into the earth. So you can't just call it conservation just amongst your spoon and your head. It has to be the whole. So for the whole universe, the electric charge is conserved. What is quantization, right? Quantization is, well, it's in the name, this quantity. How do we define the quantity of electric charge? Now, when we have length, we can have it in the units of meters, right? Meters, or centimeters, decimeters, millimeters. So you could say, well, I need 10 meters of a rope, you could get it. If you say I need 20 meters, you could get it. But what about charge, right? So we know that we're using electrons in electricity. So let's deal with electrons for now. So let's say I try to get charge from somewhere. I could get 1 E worth of charge. Well, E is electron, right? So let's say I'm trying to buy it. They could give me 1 electron and I have 1 electron worth of charge. Can I ask for half an electron worth of charge though? I don't think so. But if it's length, let's say it's a rope, I could say half a meter, 0.2 meter, 0.25 meter, 0.001 meter, you could get it, provided you cut it accurately enough. But here you can't. You can't get half an electron worth of charge unless you have subatomic particles that have smaller units of charge. But then again, it's quantized in the sense there's set steps, right? So since I could cut length anywhere, it's this way. For example, this is the length. I could just cut it wherever I want. You increase it just continuously. Even if you zoom it in, it's still a gradient. But for electrons, it's like, for charge that is, 1 electron worth of charge. If I add another, the charge is now 2e, 3e, 4e, 5e, and so on. And even if I have a subatomic particle, maybe like e by 3, 2e by 3, 3e by 3, but you can't create 0.1e. You can't take an electron and cut it into half or into 10% and 90% of an electron. It's not possible. Well, as of now, it's not possible that I'm aware of. And I think in the context of your book, it's out of the question. It doesn't exist. So charge is quantized. And we have a unit of charge, just like we have for length in the terms of meters, we have something called coulomb. Right? Coulomb is a unit of charge. And it's named after a scientist, of course. But what exactly is coulomb? Is it a large value? Is it a small value? Well, how do we say that? Well, one electron, right? One electron has a charge of 1.6 into 10 to the negative 19 coulombs. So a coulomb is a very, very, very large value. So you might be thinking, okay, how many electrons are there in a coulomb, right? Well, let's find out. We know that one electron is this many units of charge in terms of coulomb. So how much electrons are there in 1 coulomb? So let's just do this. We have 1 divided by 1.6 to the 10 to the 19, negative 19. So this should give us into 10 to positive 19. And if you take it to the other side, around, it's in the order of maybe 10 to the 18 electrons. Well, it's not exactly 10 to the 18, but it's approximately 10 raised to 18 electrons worth of charge. It's in that order, so maybe 6 into 10 to the 18 or 7 or something like that. But it's a pretty high number. So we'll be mostly dealing with units such as microcoulombs or nanocoulombs or millicoulombs, even though I don't think it's going to go that high. But those are just this particular value into 10 to the negative 6, 10 to the negative 3, 10 to the negative 9, depending on what unit you're going to use. Now, to demonstrate how big this particular coulomb value is, let's do a pretty simple example, right? Let's give you a scenario, and this is the same example in your textbook. So the example states, if there are 10 to the 9 electrons, if 10 to the 9 electrons move from one body to the other in 1 second, per second, how many seconds or how much time is it going to take to charge one body? Okay, let's define this. One body, another body, this is supplying 10 to the 9 electrons worth of charge every second. So how much do you need to fill this up to 1 coulomb, right? So that's a pretty high value. That's actually 10, let's see, 2, 3, 4, 5, 6, 7, 8, 9. That many electrons. So yeah, is it correct? 2, 3, 4, 5, 6, 7, 8, 9. Yep. That is 1 billion electrons per second, every second, right? So it's bound to be fast. Now let's find out. So this is the rate, 10 to the 9 electrons per second. So how do we deal with this? So we know that the rate's given, 10 to the 9 electrons per second. How much time does it take to fill up to 1 coulomb, right? So how much charge is transferred in a second, right? We know it's 10 to the 9, but we need to multiply it with the value of E to convert it to coulombs. So we multiply it with 1.6 into 10 to the negative 19. Well, the actual value is 1.602. It's a pretty big value, but I think this would give us a good idea enough. So 1.6 into 10 to the 19, this is going to give us the amount of charge transferred in 1 second. And how many seconds do we need to transfer it? 1 particular coulomb. So 1 coulomb divided by the amount that we're going to charge in a second is going to give us the number of seconds. right? This is the coulombs, this is coulombs per second. So ideally, it should just give us the value in seconds. So we have 1 over 1.6 into 10 to the negative 10, which is 10 to the 10 by 1.6. So I'll just find the value, 1 by 1.6. So we would have 0.625 into 10 to the 10 seconds. So how much is that, right? It's a big value. So that would be 6.25 into 10 to the 9 seconds, which is again a very big value. So how many seconds are there in an hour, right? 1 second, 60 seconds in a minute, 60 minutes in an hour, so 60 into 60, 3,600. So if you try to divide it with 3,600 to find the number of hours, it's not going to be anywhere close. What about how many days, right? 24 hours? Still looks very imbalanced on the top. So let's have how many days, and how many days in a year? 365 days in a year. I'm not going to move to decades. I think let's try to find out how many years is it required to charge it up, right? So I'm just going to use a calculator. I could divide it right now, but let's just use a calculator for simplicity's sake. 10 to the 9, 365 into 3,600 into 24. So it says 198 years, 198 point something, but it's going to take around 200 years to charge it up, even though there's a billion electrons moving per second. So you think this should give you a perspective of how big this value is, this Coulomb value, and so we won't be using it. Maybe on a large scale, since we have a lot of electrons per body, it's useful to use this big value, but I don't know, right? Another example that's given in your textbook is to evaluate the number of electrons in a glass of water. Maybe not the number of charge, right, positive and negative, in a cup of water, right? And this question should give you some perspective into, what other types of charges we're dealing with for a macroscopic body. So a glass of water is something that, we use every day. We could see it. It's not something as abstract as, assume a point charge, right? So what kind of values are we dealing with? So let's say a cup of water is maybe 250 grams, or you could use 200. It really doesn't matter. The book uses 250, so I'm just going to use 250. So 250 grams, right? So 250 grams of H2O. Now this is a bit of chemistry, right? H2, there's maybe 2, and O is 16. So 18 grams of water in 1 mole, right? 1 mole of water weighs 18 grams. So let's find out how many moles there are. So if you don't know what moles are, I'm assuming you guys know it, but if you don't, it's the amount of substance. So it's like saying a dozen, right? So we know that 1 molecule of H2O has 1 oxygen atom and 2 hydrogens, and we know that the hydrogen has 1 electron and the oxygen has 8 electrons. So this should have 10 electrons, but we don't know how many molecules of H2O are there in 250 grams of H2O, and that's what we're using this calculation for. So 1 mole is around 6.022 into 10 to the 23. Yep, it's 6.022 into 10 to the 10 to the 23 electrons, right? Oh, yeah, that many molecules, and that has a weight of 18 grams. We know this. There's the way to find out that it's 18 grams is in chemistry. I won't be explaining that, but well, to give you a basic idea, it's like the atomic mass Okay, the atomic mass of this is 18 units. So 1 mole of this would have 18 grams, right? So if the weight of a molecule is X atomic units, the weight of 1 mole of that molecule is X grams, right? I'm just going to go with that. So to find out how many moles are there, we need to divide it by 18, right? Of course, because every 18 grams is 1 mole. So how many times do we have to divide it? Oh, how many moles do we have to have? So 250 by 18 would give us 13.88 or 89 moles. So how many electrons or how many molecules, right? 13.89 into Avogadro's number into 10 to the 23. That would give us, let's say, 8.36388 into 10 to the 24. Right? It makes sense because this is of a tens value, this is of a ones value, so 1.39 into 6, the 10 gets carried over to 24. But okay, I'm using a calculator. I don't see the point in calculating it manually since I'm explaining it, but I think the textbook and the syllabus requires you guys to do that. If you guys want me to calculate it manually every single time, just let me know in the comments. Because I was just explaining the concept, so I just thought I'd use the calculator. But when it comes to because it's just a simple calculation. When it comes to something complex like let's say we move into a chapter where we need to use something like integrals or we need to use something big, I won't be using the calculator. I'll show you the steps. But I think this is just basic multiplication, and well, I don't need to get into it. So these many molecules, right? That many molecules, and each molecule has, well, how much charge does it have? 1 electron, 8 electrons. So 10 electrons. So I could say 8.36388 into 10 to 25 electrons. And also, the positive charge would have to balance it out because water is not charged. It's neutral. So we'd have this much worth of positive as well. So negative and positive. And to convert it into coulombs, we need to divide it with the elementary charge. Oh wait, no, in this case, since we have electrons, we need to multiply with the elementary charge. So we have 1.6 into 10 to the negative 19. So yeah, into 1.6 into 10 to the negative 19. We would have I'm just going to approximate it. Let's say 133 and 38. Let's say 134 in let's say into 10 to the 4. I think so. 1.34 into 10 to the 7. Yeah. So that many coulombs worth of charge. So you could see that in a macroscopic scale, the coulombs is a small value, right? A glass of water has 10 to the 7, like a million coulomb worth of charge in it, and well, positive and negative, so it neutralizes and it gives us 0, right? It's like the additivity property. You add in 1.34 into 10 to the 7, and you give in negative 1.34 into 10 to the 7, they make it 0. So on a microscopic scale, coulomb is a huge value. On a macroscopic scale, it's not very big, but we won't be dealing with, let's say, a completely charged glass of water, right? So I think in the place where we would need it, like we're dealing with maybe a glass or a glass jar that's where maybe charged, or maybe an electrical conductor sphere that is charged, we have to deal with smaller values of coulomb. So I'll let you guys, figure it out amongst yourself, whether it's too big or too low. We won't be needing that as far as the textbook goes, but well, you could just always discuss, you could always just think about it, right? Think about it more to see, is it right? Do we need to change it? Well, a lot of work has been done already on this, but maybe if you find a better way, you could, I think. But yeah, that would conclude our lecture for today. The next lecture would have Coulomb's law and all the things that are basically mathematical, things that would define the behavior of it further quantitatively. And yeah, so see you in the next lecture. Thank you. If you have any questions, if you have any suggestions, if I'm going too fast, maybe too slow, maybe in a way that isn't very simple, just let me know. I'm trying to make it as simple as possible. And if I'm not doing it, I need to know, right? I need to make it even simpler. And I'll work on it better if I need to. And thank you so much. Bye bye.